Hi, this is Aaron Lewis from Franklin Maths. This is the next video in the normal distribution series. This lesson focuses on modelling and approximating the normal distribution. Okay, so I've got a frequency table here. I've got continuous data. This should be grams up here. And then I've got the frequency density. Now, frequency density in this case doesn't matter too much because I've got equal class widths. Okay, so I've drawn a histogram for the data. Sometimes it's just easier to see things visually. And the question we've got to ask ourselves is, would this approximate quite well to the normal distribution? So there is the graph of the normal distribution, and hopefully you can see it looks nothing like the shape. It would have looked pretty good if this one here was significantly higher. Okay, that would have been quite nice. But however, we've got two modes in this case. Okay, and you can see that from the data there. We've got a couple of modes, and we know that from the normal distribution we do have a single mode. So in this case it's not appropriate. We've got two modes, although it is, it is almost symmetrical, which this one is. We've got two modes, so we can't approximate it. And the next one, this time again we've got I've gone for the same data. I've just manipulated it again ever so slightly, and this again looks sort of as if it's getting there, and then all of a sudden it disappears. Okay, it falls off this sort of cliff edge. There's a huge sharp drop here. Again, if we grab the normal distribution curve, it just won't work for this one here. So you can justify it by eyesight, but the examiners want that. The examiners want something along the lines of the data sort of falls off as a sharp cutoff, or falls off a what I call a cliff edge, but that's just me using an analogy there. And with the previous one, they'll be looking for something like a single mode. Okay, so that's your reason for those two. Okay, now if you're using summary statistics though, okay, so remember from the first year, for ungrouped data, this should be one of the very first things you learn. For ungrouped data, the mean is the sum of the data over the number of pieces of data. You've known that for a long time, but maybe not formalized it as we did in the first year. And then the standard deviation, and I've gone for this formula because I think for me personally it's slightly easy to use. There isn't so much to remember. It is quite nice to use as well. They do tend to in the exam give you sort of sigma x squared there. So that's for ungrouped data. That's where you're just given the data as sort of raw numbers. And if it's grouped, so in a table, we would use the sigma x f over sigma f, and then it said the formulas are extremely similar. Okay, so this sort of question you would get. So we've got 60 Labradors. We've measured the mass of them. We've got a nice heavy dog there. We've got a light dog. And then we're given some summary data. Now I'm going to involve some year one practice in here as well. So it's always nice to find, go back and revisit things and find things out. So first thing we're going to do is going to try and find the mean. So we know that x bar is equal to sigma x over n. Now hopefully you spot that this isn't group data here. The dogs haven't been grouped into 27 to 30, etc. Okay, so in this case here, x bar is going to be 1920 divided by 60, which comes out as 32, I believe. Okay, so that's the mean mass for the Labradors. And then what we're going to try and find is sigma, but I'm going to find sigma squared first. I'm going to try and find the variance first, and then I'll square it at the end. So that's going to be sigma x squared over n, so sigma x squared over n minus the mean squared. So sigma squared is equal to 61680 over 60 minus 32 squared. So the variance is equal to, and I'll do this with my calculator, 61680 divided by 60 minus 32 squared comes out as 4. So the standard deviation there comes out as 2. Okay, so how does this help us answer the question? Well, we know from the normal distribution here, if this is the mean, this is the mean plus a standard deviation, this is a mean plus 2 standard deviations, and plus 3 standard deviations on that one, and then the same on this side, so minus a standard deviation, minus 2 standard deviations, and minus 3 standard deviations. Okay, now we know within the sort of plus or minus 3 standard deviations, it gives us 99.7% of the data. So it's fair enough for us to say that if something is more than 3 standard deviations away from the mean, it's an outlier, or therefore the normal distribution wouldn't be appropriate for it. I mean, you could look at this data and go, well, the heaviest dog's 45, it could be an outlier, could get rid of it, but we don't know enough about the information, so all we're doing is working on from what we know. Okay, so let's take the mean then, which is 32, and then I'm going to add and take away 3 standard deviations and see if there's a dog in there which doesn't fit. So 3 sigma in this case is going to be 3 lots of 2, which is 6. Okay, so the sort of range to make this appropriate, so 32, so add on 6 to that is 38, minus 6 from that is 26. Okay, so if to use a normal distribution, I'd need to be looking at have dogs in between the range of 26 and 38. So the lightest dog is 27, so that one's fine. But the heaviest dog there is at 45, so no, it's not appropriate. No, as we a dog which is greater than plus 3 standard deviations. Feel free to write that in proper English. I've just run out of space there, but hopefully you can see in this case here, normal distribution isn't appropriate because we've got a rather heavy dog there. We could have had several dogs at 44, 43. Again, we don't know enough about the data. We're just going from what we know, which a lot of statisticians do, and then if we spot anything, we'll drill down a little bit further. Okay, so to summarize those couple of bits and pieces there, if you want to apply the normal distribution, this is what we'd expect to see. So we'd have a histogram which is approximately symmetrical as a single mode. There's no sort of sudden drop off, or what I call a cliff. And if you're using summary statistics, make sure that most of the data is within 3 standard deviations of the mean. Okay, and that was something that we looked at as well in the first year in terms of outliers. Okay, so with those 2 pieces of knowledge, could you complete questions 1 to 4 from exercise 21D? Pause the video, do those questions, mark them, and then we'll move on to the next bit. Okay, so the next little subtopic in this is then approximating the binomial to the normal distribution. Now, the binomial distribution is studied quite a lot in the first year. It's looking at discrete data, and some of you might be thinking, well, how can you approximate a discrete distribution to a continuous distribution? Now, we can do that. We'd need to do something called continuity correction, but that isn't part of our course. It is in the further maths module, and it was in the old A-level course as well, in the S2 module. So today we won't be applying continuity correction for those statisticians watching. We will just be approximating. Okay, so I'm going to pull up an animation which will show you what's going on. We'll have a look at it, and then we'll sort of summarize what we can see. Okay, so I've loaded up GeoGebra. This has been made by George Stair. Thank you for that. And this is a normal distribution here. Sorry, not a normal. This is a binomial distribution here, with my number of trials being 60 and my probability of success in this case is 0.5. So it could be throwing a coin 60 times. Now, if you have a look here, this does look very much like a normal distribution. If I just click the normal curve there, look, it looks almost bang on. It's pretty good. And we'd expect to peak at 30, wouldn't we? If you tossed the coins 60 times and half chance of getting ahead, you'd expect, we're talking about expectation or the mean to be approximately 30 times that we get ahead. So that's pretty good. Now, if we begin to move these sliders along, look, again, that still looks pretty normal, to be honest with it. If you can see that, it still looks like a normal distribution. So what we're going to do is just play with the sliders and see if we can force it to not be a normal distribution. Okay, so if I keep sliding this over here, it still looks pretty much like a normal one. Again, well, close there. And as we move over, look, that wouldn't be appropriate there. Okay, you can see that you've got this huge cliff here, so that certainly wouldn't be appropriate. Moving along to the other side, again we've got this huge cliff here. So just playing around with the p-value there, the probability success value, you can see that we sort of lose the ability to approximate this at extreme values. Now I'm going to move the number of trials. So if you have a look, low number of trials, again, looks this, some of this really isn't appropriate. So it seems to me like when you've got a low value of n and a low value of p, it isn't appropriate. Look at that, that's not appropriate at all. Is it 4 trials? And look, using a small value of n, look, none of this looks normal at all. There's no normal curve on that, which seems appropriate. So there must be some sort of criteria for us to approximate this. Now the proof of this isn't in this course. I mean, feel free to go look that up. But I won't be covering that now. I would just be giving you the necessary conditions. So hopefully you've seen that and gone, oh yeah, look, it looks normal, but how do we know? So I'll just pause the video quickly, dive back onto PowerPoint and show you. Okay, so let's have a quick look at the conditions. Okay, so if we've got a binomial distribution, and remember from your first year, n in this case is the number of trials. P in this case is the probability of success, or whatever you're trying to achieve. Okay, as long as n multiplied by p is greater than 5, and remember from the first year, that is the mean of a binomial, and n 1 minus p is also greater than 5. So remember, 1 minus p would be failure in this case. When I did A-level maths, I used q as 1 minus p. You can use that if you want to. So if we've got those conditions, we can then make a normal distribution. Now we can't use x again, but we can use a y. So you would have np, which was the mean of the binomial, and we'll give that the Greek letter mu. And here it's not quite the same as this, so just be careful there. This here is the variance of a binomial. Okay, so just be careful this. I think in your exam, if this came up, it'd probably be about 1 marker saying, so-and-so wants to approximate this binomial to the normal, are the conditions satisfied? It's probably going to be 1 mark or something like that. It might actually give you the formula for this as well if you're lucky, but it's worth remembering. That's easy to remember. This isn't too bad. It's just like, if you remember it as NP and NPQ, that's what I used to do. And 10 or so years ago, it was nice and easy to remember like that. Okay, so I've got a bias coin. I'm going to throw it 500 times. The probability to land on heads is 0.7, and we're going to model it and then work on it. So A is why can this be binomial? B is could the normal distribution be used? Can you justify it? C is then to work out probability. D is also to work out probability, and E is to explain why C and D are different. So let's work through those. So if you want to pause the video, jot those down now, or you can watch me do it. Anyway, it's up to you. But just look at the structure of the questions here. It looks like an exam question. Okay, so let's have a look. So why can't the binomial be used? So this is just good practice, a bit of retrieval practice for you. So the first thing then is we have two outcomes. And if this was an exam question, I would always be putting these back into context. Two outcomes, heads or tails. The next one then is we have a fixed number of trials. And in exam spec, you need to be stating what those are. Always put these back in the context. It's easy marks. Next one then is the coin throws are independent. Independent trials. And you might want to put that in context by saying one throw of a coin doesn't affect the next one. And the last one then is a fixed probability of success. So you've got a fixed, whatever you want to say, or you might say the probability of heads is fixed. Okay, because if it changes, it doesn't fit into the binomial. So that's a nice little bit of revision for you. Part B, can the normal distribution be used? Well, we need to check the conditions then, don't we? So can you remember what they are? Well, it was NP. Let's work out what that is. N multiplied by P, so that's 500 times 0.7. Which is equal to 350. And the other one was N1 minus P, which is equal to 500 times 0.3, which is then equal to 150. Okay, so then all we need to say is, as NP is greater than 5, and N1 minus P greater than 5, we can use the normal distribution, or we can approximate. I'm just rushing here because my handwriting isn't great on this tablet. Okay, nice and easy to do. Right, the next bit then, same question, and what I want you to notice now is these two questions look extremely similar, but there's a bit of a difference. Okay, now because we're using x here, now up here, this is a binomial. So what we'll be doing here then is x is approximated by the binomial distribution, and remember it's NP, so it's 500 trials, 0.7, a little bit of calculator practice, a little bit of revision here, so I'm going to grab the calculator. So let's have a look. 1 second, I don't know why I put an equal sign in there, so not concentrating. We'll just state the conditions. Probability that x is less than or equal to 340. In the original video for this one, I have changed this. I did have 300, but the probability comes out ridiculously tiny, so it made sense to change it. So we're going to go over to stats, distribution, and it's binomial. Now, it's a cumulative probability when all the values from 0 to 340. So using the BCD button, it's variable data. My low is 0, my up is 340. We're doing 500 trials with a 0.7 chance of getting ahead. So let's have a look what it comes out as. So I'm going to take it to 4SF, so 0.1767. So 0.1767. So apologies for the 0 there. There we go. Okay. Nice and easy to do. Nice bit of revision. Okay, so we know that the normal distribution could be used. So let's write down the actual approximation then. So it is NP. In fact, let's work them out over here. So N times P, which gives you the mean of a binomial. So that's 500 times 0.7 gives us 350. So mu then is equal to 350. If I'm going over the top of my workings, I like to do that and be really explicit with everything. And the last one then was the variance. Remember, that's sigma squared, which is equal to 500 times 0.7 times 0.3. So sigma squared then is going to be equal to 500 times 0.21, which I think is 105. And probably worth me writing there what sigma then is. Root 105, there we go. So let's have that as 105. Okay, so the probability that y then is less than or equal to 340. Let's grab the calculator and see what's going on. So exit from there, exit, distribution, normal. Again, it's another cumulative one. Still got these nice numbers in, which is quite good. So my sigma here is root 105. My mu is 350. So I get 0.1646. 0.1646 if my eyesight. Okay, so the question is then why are these two different? Apologies if there's a bit of a judder there, but just quickly edit the recording. Okay, why are these two different? Well, we know this one gives us the proper answer. This is the exact answer here. Now this one gives us an approximation. And the reason for that is that the normal distribution here is continuous and the binomial is discrete. And there you go. So that's well worth putting in there. So the binomial is discrete and the normal is continuous. And it's not on this course, but continuity correction, those of you that are watching this going, where's the continuity correction? That isn't part of this course, that is in the further maths course. Okay, so here's a quite a good question. There is lots and lots of maths in this, lots and lots of reading. It's one of my made up ones, so it might be a bit convoluted, but I think it's worth looking at. Okay, so we've got a city which claims it's got a high proportion of grade 4s in maths compared to other cities. We've got a sample of 1,000. Look at who's got a grade 4 or greater, look at hypothesis test, and then work from there. Okay, so I'm going to write this down, and this thing is in here. They're asking us to use the normal distribution. We could have done this binomially and sailed off into the sunset and said thank you for the marks, but they're asking us to use the normal distribution, which they could do in exam, just because they want to add a couple of marks on or something like that. Okay, so let's have x equal. Let x be the number of grade 4s or higher. Okay, so the number of people that get grade 4 or more. Okay, just going to drop a line down the middle. So this is effectively a hypothesis test. Well, in fact, more than a hypothesis test, it's actually a critical region test. We're actually trying to find a critical region here. So let's have. We know this is binomial. You can check it's binomial. Matters for the conditions, which obviously we need to make some assumptions, but we know x is approximated by the binomial distribution. Some sort of value of p here. And because of the hypothesis test, we have the null hypothesis here that p is equal to 0.8. That's where the probability is still the same. H1, well, if they're claiming that they've got a higher proportion, it's greater than 0.8 then. And what we're trying to calculate then is a probability that x is greater than some sort of value is equal to 0.1, which makes this into a sort of critical region question. Okay, and that's where x be 1000 0.8. So it would be great to just do this binomially and just get on with it, but this question has forced us into using the normal distribution. So let's work these out then. So over here on the right hand side, we're going to be using the normal. So let's work some things out. So the first thing then is to check that the normal can be used. So NP is just going to be 800. It's easy enough to work out. And N1 minus P is going to be equal to 200, both greater than 5, so it can be approximated normally. So we know that mu then is equal to 800, and then we need to work out the variance as NP1 minus P. Not fall into the trap of thinking these two are the same. Okay, which comes out as 160. So X is approximated by the normal distribution. I should have changed this to a Y actually, it's a bit naughty, let me change it to a Y. There we go. So 800, 160. We know that mu is equal to 800, and we know that sigma is equal to the square root of 160. You've got highlighters, highlight all these little bits and pieces here. So what we're going to try and find, draw a rough, very rough normal distribution curve. Mean is down the middle. We're trying to find basically the top 10% here. Trying to find out what number would we need to get for us to reject the null hypothesis. Okay, so we're doing this normally rather than binomially, and then we'll compare answers in a second. So let's grab the calculator and see what's going on. And there it is. Okay, so into stats mode, just X out of that. Distribution, normal distribution. It's a cumulative probability, or is it an inverse? What is it? It's an inverse in this case. I've got a right tail, an area of 0.1. I have a mean of the square root of 160. Sorry, a standard deviation, not a mean, and a mean of 800 there. So approximately 816.2 people, but this is talking about people here, so we're going to have to take the 816. So we need 816 people for us to reject the null hypothesis. I'm just thinking in my head they should have taken 817, but I think 816 is right. I mean, I'd normally round it to the nearest one and then justify it. Again, we can check this with the binomial now. It doesn't quite like this when I put this in, but let's see. So just go to stats mode, exit. Let's get a binomial up. Let's get an inverse. Let's get 1,000 trials. Let's get a p value of 0.8. And I've done the wrong tail there. That would be the so let's go for an area 0.9. And there you go, it does actually give me 816. So you can see there, that one works really neatly, that if you use the binomial or the normal there, it does actually work and give you the 816. So that's quite a nice little question to look at. It's something that in an exam would look really, really difficult to do, but it's not horrendous, and hopefully that makes a bit of sense. Okay, I'm going to ask you to complete questions 5 onwards from exercise 21D. Any questions, send me a message. There are work solutions with the exercise as well. Thank you for watching, and good luck.